Hello, welcome to next chapter of strength of material. Our topic is theory of failure. In this chapter, we will consider the working stresses of the material and compare the material with the test specimen which has already failed. Okay, and different criteria for its failure has been assumed. Okay, and according to which the theories are named. So the first theory is maximum principal stress theory or Rankine theory. In Rankine theory, the ultimate stress is the failure criteria. Okay, or principal stress is the failure criteria. This is the working specimen. Okay, and this is the test specimen. Okay, so here in the working specimen, sigma x, sigma y, tau x, y are active. Okay, or a complex system of stresses is acting. Okay, now we will find out the principal stress in the working specimen, and okay, one we will find out principal stress in working specimen and a test specimen which has failed, which is subjected to failure. We are assuming that it has failed due to ultimate stress. Okay, so the maximum principal stress should not exceed this stress. Okay, this stress we will measure the ultimate stress of the test specimen and we will calculate the principal stress of the working specimen. Okay, so this working principal stress or working maximum principal stress should be less than this ultimate step to avoid the failure of the working object. Okay, so in this case, where sigma x, sigma y, and tau y, x, y are acting, okay, the maximum principal stress is sigma 1 is equal to sigma x plus sigma y by 2 plus 1 by 2 root sigma x minus sigma y square plus 4 tau x y square. Okay, and it should be less than sigma ultimate. So sigma 1 should be less than sigma ultimate, and we provide its failure. The provided failure we introduce a new term that is factor of safety. If we divide ultimate stress divided by factor of safety, then it will be equal to the working stress. Okay, so the working stress should not exceed sigma 1 or provided its failure. Okay, so I read out for you. According to Rankine theory, maximum stress in any object subjected to stresses sigma x, sigma y, and tau x, y should not exceed the ultimate stress of that object when tested in universal testing machine. Okay, so this is the maximum principal stress theory. Okay, and its graphical representation is okay. It is represented by a scale. Okay, how we are taking that sigma t and sigma c are maximum tensile and maximum compressive stresses, and we are assuming that uh, these are the these are same. Okay, maximum tensile which that material can be subjected to. Now both we are assuming that both are equal maximum tensile stress and maximum compressive stress and equal to sigma star. Okay, so in one direction uh, the maximum principal stress, that is sigma, if maximum principal stress is sigma 1, should not exceed sigma star. Okay, so this sigma 1 should remain within this scale, and if it is compressive it should remain this. Likewise, when if the sigma 2 is the maximum principal stress, then its limit should not exceed from this, and uh, if it is compressive, maximum compressive stress, then it should not exceed this. So the material within this sphere when the material is subjected to the stresses within the sphere, that is less than sigma star in one direction and less than sigma star in other direction. Okay, then the material is safe. Okay, so these these region represent the working stresses of the specimen, and in this region outside the sphere, there the material will fail. Okay, so sigma 1 should be less than plus minus sigma star, and sigma 2 should be less than plus minus sigma star. Okay. So this is the graphical representation of readout. Okay. Maximum tensile or principal stress is sigma D star is equal to sigma star. Maximum compressive principal stress sigma C star is equal to sigma star. For actual specimen, sigma 1 should be less than plus minus sigma star, and sigma 2 should be less than plus minus sigma star. The principal stresses are drawn on x-axis. This is the principal stress. Because it should be less than principal stress drawn on x-axis and should be less than the principal stress can be this much, and maximum value is sigma star. Okay, it should be less than sigma plus minus sigma star sigma or sigma t or sigma d. The second principal stress is down on y-axis. Okay, it should be less than this. Sigma star is equal to sigma t plus sigma c. So the stresses in the direction of sigma 1 and sigma 2 should be less than the ultimate stress in both compression as well as in tension. The point within the graph is in safe condition. It is clearly safe condition. Next theory is maximum shear stress theory or theory due to gust or Tresca. Generally, it is called Tresca theory. Okay. So again, this is the working specimen and is subjected to same stresses, that is sigma x, sigma y, and tau xy. And this is a test specimen, and it is again failing in at a yield stress or ultimate stress. But we are assuming that it is not failing due to the maximum ultimate stress or maximum yield stress. It is failing due to shear stress. Now, the shear stress in this specimen will be it is the maximum principal stress. If you consider this, okay, this is the maximum principal stress and minimum principal stress is 0. So the shear stress will be maximum principal stress minus minimum principal stress divided by 2. So it will be sigma equal to 2. That is equal to K. And here the principal stress will be maximum principal stress will be sigma 1, um, sigma 1 and sigma 2. Maximum and minimum principal stresses we are assuming that sigma 1 and sigma 2 are the maximum and minimum principal stresses. Okay. So the maximum shear stress will be sigma 1 minus sigma 2 by 2. Okay. We can find out sigma 1 by using the formula sigma x plus sigma y by 2 plus minus root sigma x plus sigma y square uh, plus 4 tau x square. Okay, we can find out sigma 1 and sigma 2, and then we can find out sigma 1 minus sigma 1, 2 by 2. Okay, so it is the maximum shear stress in this specimen, and maximum shear stress in this specimen is sigma yield by 2. So this maximum shear stress should be less than maximum shear stress in test specimen. So to equate these two, we introduce factor of safety. Sigma 1 minus sigma 2 is equal to sigma yield by f1. Okay. Now the graphical representation of maximum shear stress theory. Now the graphical representation of maximum shear stress theory. Okay. Take first quadrant. Okay. This is the first quadrant. This is y-axis. This is x-axis. Draw maximum principal. Sorry. Draw one principal stress on x-axis and other principal stress on y-axis. Okay. If both are positive, if sigma 1 is positive and sigma 2 is positive, then it will be on positive axis and it is also on positive axis. And when both are positive and third stress can be assumed as 0. Okay. So when both are positive, then uh, then one of them will be the maximum. If it is the maximum principal stress, okay, then the minimum principal stress will be zero, okay, and minimum principal stress will be zero, okay, and the maximum shear stress will be sigma 1 by 2. So maximum shear stress will be the function of sigma 1 only. Okay. Okay. Now if sigma 2 is the maximum principal stress, okay, sigma 2 is the maximum principal stress, okay, then and sigma 1 is minimum is other positive principal stress, but it is less than sigma 2, okay, then the minimum principal stress will be 0, okay. So in this case, sigma 1 by 2 is the maximum shear stress, okay. If we consider this as maximum stress, if we consider this the as maximum shear stress or maximum principal stress, the maximum shear stress will be sigma 2 by 2, okay, sigma 2 by 2. Then the and maximum shear yield stress is sigma yield by 2. So then 1 sigma 1 maximum can be equal to sigma yield. Okay, this is sigma yield, sigma star is sigma yield. Okay, and similarly, the maximum sigma 2 can be also sigma yield. Okay, so this line is parallel to x-axis and this line is parallel to x-axis. So this graph is a here in the first quadrant reading out for you. In the first quadrant, sigma 1 is the maximum principal stress. Okay, sigma 1 is the maximum principal stress. Here is only, okay, in one direction, and sigma 2 is the principal stress in other direction. And third principal stress is 0. Sigma 1 and sigma 2 are both positive, so both cannot be maximum and minimum, as minimum principal stress is 0. Okay, four line OA, four line OA, four line OA. Okay, sigma 1 by 2 or sigma yield by 2 or sigma star by 2 is the maximum shear stress. Okay, the maximum value of this sigma 1 can be sigma yield. Okay, and sigma 1 can vary from 0 to yield. Okay, if we don't take any factor of safety, then sigma 1 will be equal to sigma yield. Okay, similarly, 4 line OD, 4 axis OD. Okay, 4 line OD. That maximum shear stress is sigma 2 by 2, sigma yield by 2. That is should be equal to sigma yield by 2 according to shear theory, and it should be sigma star by 2. So sigma 2 maximum can be equal to sigma star if we don't take any factor of safety. Sigma 2 can vary from 0 to yield. So B and AE will be parallel to OA and OD. The same graph will appear in third quadrant also. Okay, third quadrant also, because here both are positive, here both are negative. So they cannot be maximum and minimum principal stress, and like in this, okay, like in first quadrant. Okay, now if we take second quadrant, okay, one is positive. If we take, okay, one is positive and other is negative. So maximum and minimum principal stresses. So these are the maximum and minimum principal stresses. Okay, because one is positive, that will be maximum principal stress, another is negative, that will be minimum principal stress. So the maximum shear stress will be sigma 1 plus sigma 2 by 2 is equal to sigma star by 2 or sigma yield by 2. So this graph will not be line parallel to x-axis or y-axis. Okay, so because it is taking the effect of both sigma 1 and sigma 2, so graph will be like that. Okay. Similarly, in fourth quadrant, graph will be like that because both the stresses are of opposite sign. Okay, both the stresses are of opposite sign. So CD and AB are blind. Next theory is maximum principal strain theory. Okay, according to this theory, the maximum principal strain should not exceed the strain that has occurred in test specimen while failure. Okay, consider a block that is subjected to sigma 1, sigma 2, sigma 3. That is these are the working conditions. And this is the test specimen and that has been failed. So here the strain is sigma ultimate by E. Sigma ultimate by E. And here the working here the here the maximum if sigma 1 is the principal stress, then the maximum strain is sigma 1 by E minus mu sigma 2 by E minus mu sigma 3 by E. So this maximum strain should not exceed the failure strain. Okay. So two-dimensional graphical representation of maximum principal strain theory. So in the first quadrant, similarly, likewise, okay, in the first quadrant, both stresses sigma 1 and sigma 2 are positive. Okay. Now, if sigma 1 reaches up to sigma ultimate, okay, and then it will extend the material. Okay, then sigma 1 will extend the material. But sigma 2 is also tensile in nature in first quadrant. So it will compress the nature. So this graph, so at this point, the sigma 1 can be more than the sigma ultimate. Okay, because sigma 2 is compressing the material to bring the same strain. Okay, so the graph will be slightly inclined like that. Okay. Similarly, for J uh, point J, both are of negative. Both are negative. Sigma 1 and sigma 2 are negative. So J should be like this. Okay. It will be it will be having more stress than the ultimate stress. Okay, one of the stress. Okay. Okay. So these because here sigma 1 is increasing length and here sigma 2 is decreasing the length. Here sigma 1 is decreasing the length and here sigma 2 is increasing the length. Okay, so we read out, but in the sorry, in this, in these, both are opposite in sign. Okay, so their effect will be same. Okay, so this will be H will be slightly towards y-axis or towards x-axis. Similarly, L will be slightly towards y-axis and towards x-axis. Add sorry, read out. Add point A B C D. A B C D. Add point A B C D. Represent the bar subjected to one principal stress only. Okay. At point A, there is no, there is only sigma 1. At point B, there is only sigma 2. At point C, there is only sigma 1. And at point B, there is only sigma 2. Okay. So the maximum principal strain will be sigma 1 by E at point A. Okay. At point A. And at point B, it will be sigma 2 by E. Okay. At in the region OAGD. OAGD. Or in the first quadrant, both principal stresses are positive, or in this region, the value of strain is sigma 1 minus mu sigma 2 by E. Okay. So more the value of sigma 1 and sigma 2, so more value of sigma 1 and sigma 2 can be felt on the bar, as the effect of sigma 2 is to decrease the strain. Okay. Hmm. Similarly, the above effect is same in third quadrant, where sigma 1 and sigma 2 are of same opposite sign, that is of compressive nature. In the second quadrant, that I will give. The second quadrant and fourth quadrant, sigma 1 and sigma 2 are of opposite nature. One is tensile, other is compressive. Okay. So the maximum shear strain will be summation will have same effect on the material. Okay. So the maximum strain will be sigma 1 plus mu 2 v sigma 2 by E. That is E max. So increase in any of the stress will result more strain. Okay. Because both are increasing or decreasing the length. Okay. That is the graphical representation of maximum strain theory. Next theory. Next theory is maximum strain energy theory. According to the maximum strain energy theory, the strain energy under actual conditions should not exceed the strain energy. Yes. Again, consider is this working specimen that is subjected to sigma 1, sigma 2, and sigma 3, and a test specimen that is subjected to sigma ultimate. The strain energy of working specimen we have treated in strain energy article. Okay, this is strain energy of total strain energy of working specimen or specimen subjected to sigma 1, sigma 2, sigma 3. And if we put sigma 1 is equal to sigma ultimate and 2 and sigma 2 and sigma 3 is equal to 0, you can find out the strain energy of test specimen also. Okay, so this is the strain energy of test specimen. Okay, so this in this criteria in this the criteria is the this strain energy should not exceed this strain energy. So this should be less than equal to this. If we introduce factor of safety, we will divide sigma ultimate by alpha. This is your strain energy theory. Okay, so in this case we also consider two-dimensional case. Okay. So this is an ellipse. It will form an ellipse with its this is the two-dimensional energy. Okay, it should not exceed. So it is an ellipse. The Broad equation is of ellipse with a center at origin and axis at 45 degree. This ellipse passes through A, B, C, and D. Passes through A, B, C, and D. Okay, midpoint of all these. Okay, there is only the major and minor principal are active. Okay, so with major and minor axis, NM. This is the major axis of ellipse. Okay, and this is the minor axis of ellipse. Major axis and minor axis. Okay. With NM and QPR, major and minor axis. This ellipse is inscribed in the parallelogram GLK given by the maximum strain theory. This is the this this is called maximum strain energy theory. Okay, sorry, maximum strain theory, and this ellipse is inscribed within the maximum strain theory. Okay. Next and most important theory is maximum shear strain energy theory or vorticity theory or distortion energy theory. Okay. Again, we consider a specimen, working specimen that is subjected to sigma 1, sigma 2, and sigma 3, and a test specimen subjected to sigma yield. Okay. According to maximum shear strain theory, the shear strain energy that we have studied in last article under actual condition should not exceed the shear strain energy under test condition. Okay. So maximum shear strain energy should not exceed shear strain energy under test condition. Okay. So we will find out the shear strain energy of this, we'll and find out the shear strain energy of this, and this if shear strain energy should not exceed this shear strain energy. So the formula for maximum shear strain energy is this sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square 1 plus mu divided by 60, or we can say it is 12g divided by 12g. Okay, you can put the value of it. Under test condition, we will put sigma 2 and sigma 3 is equal to 0. Okay, then the maximum shear strain energy will be this sigma L square 1 plus mu divided by 3. Okay, and this should not exceed this, or we will or vacuum shear synergy of the working specimen should not exceed the vacuum shear synergy of test specimen. Okay, so it should be this. Okay, in all the above theory, sorry, in if we take brittle material and take the criteria for criteria maximum shear energy theory, then the sigma yield is replaced by sigma alpha. Okay, this is the and if we want to equate it, we have to divide ultimate by FOS. Okay. Okay. Now one more article. Uh, According to maximum shear stress theory, okay, the relationship between according to maximum shear stress theory, relationship between shear yield stress, shear yield stress, according to maximum shear stress theory, this is your maximum shear stress theory. According to maximum shear stress theory, shear yield stress, that is K shear stress is equal to normal yield stress by 2. Okay, but in this case, there is different relationship between shear yield stress and normal yield stress. Okay, how? Uh, Consider a specimen, okay, subjected to shear yield stress K. Okay, this is and because it is subject to shear yield stress, it will fail. Okay, now if we draw its more circle that we have drawn earlier, that is the case of pure shear, we'll find out the maximum principal stress and minimum principal stresses are maximum principal stress is plus k and minimum principal stress is minus k. Okay, okay. Now the shear, because these two specimens are same, both are failure, both are failing. Okay, because we are doing nothing but drawing its principal stresses. Okay, so the shear strain energy stored by this and this should be same. Okay, so the shear strain energy stored by this specimen is be put in the above formula of shear strain energy. That formula sigma 1 minus sigma 2 square sigma 2 minus sigma 3 square sigma 4. uh, This formula, okay, then you find you put sigma 1 is equal to k and sigma 2 minus is equal to minus k and sigma 3 is equal to 0. Okay, we'll find 2k square plus k square plus k square the 6 is or 1 mu 1 plus mu. Okay, or we'll solve it. Okay, it will be k square 1 by 1 by 1 plus mu divided by 6 is okay. But the shear strain energy given by the failure when it is subjected to sigma yield is we have found is given by that we have found. Okay, okay, so this is sigma yield square, that is this expression. Okay, this expression. Okay, now both are failing. This is failing when we subject the test specimen to pure shear, and this is when subject to shear resistance, and we are taking the criteria as shear strain energy. Okay, both are failing. So both the strain energy of both will be same. Okay, but okay. So by doing this, we will find out sigma yield square is equal to 3k square and k is equal to sigma yield by root 3. Okay. Now last topic is graphical representation of bone message theory. The ellipse drawn on the bone message. Uh, this is also an ellipse which is outscribed on maximum principal stress theory. Okay, the ellipse drawn on the bone message theory is for two-dimensional system with the boundary of ellipse being according to maximum principal stress theory and equation being this. Okay, the major axis and minor axis of the ellipse of GDF. Okay, thank you.